how we detect it and all that stuff, right? That's how we try to detect it. So relativistic neutrino would still not go as fast as the speed of light in vacuum. I mentioned how after the neutrino, say from a exotic, high energy event, hits the quark in the ice, it creates a particle shower, and then that particle shower goes at a speed that is more than the speed of light in that medium, producing Cherenkov radiation, but it's still not the speed of light in vacuum. So the speed of light in vacuum is still greater, and only light goes at that speed, okay? Nothing else. Yes, I know. First, they were suspended to travel at speed of light. Suspected, yes. Yeah, exactly. So at first we thought neutrinos were so low mass, we thought that they might be like no mass, but they're just low mass. They're not no mass. So they still have a little bit of mass, and there's like 3 different flavors. They're definitely more odd and more unique type of particles. And so they were a point of like, they were elusive, they still are elusive, and they were confusing, and they were actually a candidate for dark matter as well. We talked about that too during one of our live streams. Not one, many of our live streams, because we've been talking more about dark energy, dark matter lately. And basically, neutrinos are so introverted, so different, and they only interact through the weak and through the weak force, through the W and Z bosons. So they're so different, and sort of how they have evolved, or evolved as in how they went through the steps in the universe, is also kind of different, because we also have been talking about the evolution of the universe and how, in the beginning it was radiation dominated, and like the photons and electrons and positrons were all hitting each other constantly, and then neutrinos kind of detached, all that stuff, right? So neutrinos are gonna be different. How to physicists explain tensor? So tensor is just a container. So like we mentioned during the Einstein equation live, that a scalar is basically a very simple tensor. I think it's called a 0th order tensor. Actually, I have a note on this. Let me just read my note on this. A tensor is a generalized math object that represents a multilinear relationship between vectors, essentially acting as a container for data in multiple dimensions, which can be thought of as an array of numbers that describes a physical property requiring multiple directions to fully characterize it. A scalar is a 0th order or 0 rank tensor, and a vector is a 1st rank tensor with higher ranks representing more complex relationships between directions. So definitely for space-time being a four as in the number 4. F-O-U-R, 4. 4 space-time, right, is what we say for relativity. Basically, that's not the same as the Cartesian, like XYZ math that we generally do. So why this general relativity math is harder is because we are actually in a different kind of coordinate system, because even having just one extra dimension, which is the dimension of time, can actually complicate things, and you need like this metric thing defined out. G mu nu is the metric, which gives you the invariant in a 4 space-time. So that's where tensors come in physics. And for me, I mean, it's just a matrix. It's just a way to, because there's like all these different directions going on, all this multi-direction type of stuff going on. So it's not a simple equation is not going to be able to write down what I'm trying to write down. That's how I think of it. And so I need a tensor now to like write down what I want to write down, because there's like 4 dimensions, and I have to write something down, connecting all these different things and parts. But it's not too bad, because 4 dimension And the first